Today, I'm going to teach you simple and compound interest using something we all love, pi. Let's start with the formulae and variables. Simple interest has the formula a is equal to p 1 plus I times by n, whereas compound interest has the formula a is equal to p 1 plus I raised to the power of n. Notice that both of these equations have the same variables. So let's take a closer look at what each variable means. A stands for the accumulated amount, and that simply means the amount that you would result in after the interest takes place. P stands for the principal amount, or I like to call it pi. And you'll see why in just a moment. I refers to the interest rate, and n refers to the terms over which the interest rate acts. Now, I keep saying pi, but let me show you what I mean by that and why it's such an effective tool in understanding our interest rates. All right, let's look at simple interest. Our formula, as we recall from earlier, is accumulated is equal to principal, or pi, bracket 1 plus interest times by terms. Now, if you multiply this out, what you'll get is 1p plus p times I times n. And we all know that you multiply out using the rainbow method to each term in the bracket. Now, what does this mean? Well, what it essentially means is that our accumulated amount is going to be a combination of the amount we started with added to a new amount, which refers to a proportion of the principal amount times by an amount of terms. So think of it like this. You have a pie. Here's a pie. It has a nice cherry on top, and it's 100% of a pie. It's one pie. Now, if your interest rate is, say, 10%, then what this means is that it's going to take a slice of the pie that's about 10% of it. And you're going to get that 10% every term. In this case, the amount of times that n acts on the interest rate. So if n is equal to, say, 6, then you'd get 6 10% pieces of pie. It's that simple. If n was, say, 100, well, lucky you. You got 100 10% pieces of pie. And if you do the maths, 100 10% pieces is roughly 10 pies worth. So, let's put some values on this equation right here. So, as an example, let's see how many pies we can accumulate. We're going to start off with 1 pie, and we're going to make our interest rate 12.5% times 100 terms. And that simply means that this 12.5% is going to act 100 times. So, doing the maths, we're going to find that we get a value of 1, close bracket, 1 plus, now 12.5% is the same as 12.5 over 100. Times that by the 100 terms, and what we'll get is 1, bracket 1 plus, hundreds will cancel out, 12.5. And we end up with, therefore, 13.5 pies. Not a bad day, considering that you started off with 1. However, in the real world, you'll hardly get an interest rate like this. All right, you've officially graduated to compound interest. So compound interest is a bit more interesting than simple interest. And we can derive that from looking at the formula. A, or the accumulated, is equal to the principal, or pi, 1 plus the interest, raised to the power of the terms. Now, the fact that it's raised to a power of the terms makes compound interest that much more of a formidable force. Recall in simple interest, we would start off with a pi, we'd get a slice of the pie, and then the next time the interest acts on it, it'll take the same slice, or the same size slice from the pie each time. That could be 10%, it could be 99%. But the fact remains is that it's taking the same percent of the same sized pie. But with compound interest, it's an entirely new beast. You see, with compound interest, yes, you're taking a slice of the pie, but what happens is that a new pie, a bigger pie, is created because that slice that you took gets added back to the original pie and creates an even bigger pie. And this happens on and on and on. And so essentially, what you have is something known as exponential growth. In simple interest, the growth would look something like a straight line. With exponential growth, the growth would look like a curve that's getting steeper and steeper as you go along. What you'll notice is a very interesting region where perhaps simple interest will give you a higher accumulated amount than the compound interest. But over a long enough time, so as the time or the amount of terms, should I say, gets larger, compound interest will always win. Let's look at an example of compound interest. We start off with 1 pi, so our accumulated is equal to 1 pi, 1 by the interest rate. Let's make that interest rate, say, 12.5%. So we know that 12.5 over 100 is equal to 12.5%. And then let's say this acts over 12 terms. What do you think will be the result of this? Well, the result is roughly 4 1/10 of pi. Now that's a lot. You started off with 1 and you get 4. If this were merely simple interest, so let's do the simple interest calculation. So 1 plus 12.5 over 100, that's 12.5%, times the amount of terms, 12, you would get an answer of about 2.5. Now, 4 1/10 of pi is much better than 2.5 pieces of pie. I think we'd all agree on that. So, ultimately, when we're talking about pies, we're really trying to get across the idea that the money is like a pie. It's an actual thing. And it grows. It accumulates. There's slices of it. And so let's start replacing the pies with money. In our world, interest rate comes in different forms. So we've got to be wary of that. From weekly to monthly to yearly. And you've got to make sure that your interest rate and your terms are compatible. For example, you wouldn't want to be using, say, a weekly interest rate with a yearly term? Because it wouldn't make any sense. You'd have to find a way to convert the years into weeks. And luckily for us, we know that a year is 52 weeks. So, if this interest was acting over a year, we'd replace the year with 52 weeks. It's as simple as that. In this next example, we have a principal value of $100, an interest rate of 10% per month, and terms equal to 1 year. So let's work it out. Accumulated is equal to principal. 1 plus the interest is 10% per month. So 10%, that's simply 10 over 100 times by 1 year. Wait, it can't be 1 year. That's exactly right. See, 1 year is equal to 12 months. And notice that the interest rate is months. So we've got to convert the year into months. Now, using that, which is correct, we'd find that we'd have roughly 100, 1 plus 1.2. And so you'd end up having 100 times 2.2, which is 220. Good. Now you have everything you need to tackle these kinds of problems. So here's a problem that you can pause the video and attempt, or simply keep watching as we solve it together. We're finding the accumulated, which is the unknown. The principal is 125. Interest is 10% per month. And the term is 2 years. Using this information, find out the accumulated for simple interest and the accumulated for compound interest. All right, let's go with simple interest first. We know that A is equal to P 1 plus I times N. Simply plugging these values in, we put P as 125, 1, which remember just means that the original amount is there always, plus the interest, 10%, so 10 over 100, and 2 years, which effectively equals 24 months. That would give us an answer of 125 bracket 1, 24 times 10 over 100 is 240 over 100, which is 2.4. So we get 125 times 3.4, and that is equal to 425. Not bad, not bad. We've effectively tripled our original amount. Let's look at compound interest though. The accumulated is equal to P 1 plus the interest rate raised to the power of n. That would be equal to 125 1 plus 10 over 100 raised to the power of 24. Now, let's try and find out what exactly that number is. If you did the maths, this would equal 1231.21, which is 3 times larger than the simple interest amount. And this actually illustrates a very important point about our real world. In our world, you would never get a compound interest rate that is as high or equal to a simple interest rate, because compound interest grows so much faster than simple interest. So using this information, you can find out how your amount of money will grow in a set amount of time. But it could be even more fun than that. For example, with compound interest, you can sort of, within a reasonable amount of accuracy, calculate the population growth of bunnies. For example, you'd find out how many bunnies, so the accumulated, is equal to the initial population, 1 plus their interest, so that's the reproductive rate. So how many new bunnies, roughly, per an amount of time, and then just times that by the time. See, the scope of these equations are not just mathematics, and it's not just money either. So in my next video, I'll be going over higher order questions pertaining to these equations right here. Thanks for watching, and see you there.